In this video, I will show you how to do the manual fit using the two temperature model using this advanced fit option. This advanced fit, it will be an iterative process because sometimes you will define the borders too close. Sometimes you might define borders oppositely too wide, and some scans that will give you some error due to the noise and some combination of parameters way out of what you expect. So I recommend to put some decent borders, but not too much. And then, of course, physical parameters. For example, here it's from 80 to 220 thermalization time, from 200 to 900 the electron phonon coupling strengths. And usually I use couple fit. You don't have to, but it will ensure that parameters are more continuous, that you fit not just the one scan, but also some adjacent scans. The couple fit does not work for manual fit, it works only for automatic fit. Here I will not save the files after fit because it will take some time, and also I recommend not saving files after the fit for the first fit, and firstly do one manual fit, then do another fit. And for example, let's all the rest parameters, how they were defined, I already explained in the previous videos. And also, when I click fit, all the parameters will be saved. So once you open the file, you do manual fit, you are interested to do everything in one go. You to input your parameters to make sure the manual fit works, and once manual fit works, you put borders, and then you click fit all. It will take some time to fit all. And while it fits all, even though you can switch the scans in the newer version, it's not recommended because sometimes it can give you an error, even though you can see, if you see there is no fits because it fits in the process. I recommend not do anything. For example, leave at unfitted scan, and when it fitted, it will appear, and also it will appear in the status bar. While it fits, I will go quickly through the output files. For example, I have, let's go to any previous fits. Here, for example, for power dependent, I have my channel 1 outputs, and there are a lot of files. The most important files are the parameters. You can see this file here, and then the files that I show here, that are electron files with all electron temperature, file with all lattice temperature, file with modified pulse term is not as useful, but you can use it for diagnostic purposes. Then the file fit of the data is a file that how your data looks like. Additionally, I probably can open based on the previous models. I will show you the already plotted in the IgorPro all of those files, and in more details how to plot in IgorPro you can find in the presentation number 7 and corresponding video. Here I will just go through the files. For example, for one channel, then you see that this is data. The two temperature model also saves the data file, shifted data with X, for difference data versus fit, and stresses that calculated photo-induced stress. Here you see all of the files separately from parameters. You see electron temperature, lattice temperature, source term. You see your data file, then the model, you see pretty good match. Then you see the difference, the errors. Sometimes, ideally, you should see the phonon oscillations here. If you see just 1-2 periods, it's hard to say either if it's a real oscillation or if it's just some error of the model, and still you need to look how well this pattern repeats. So maybe do another measurement. Sometimes you will see the oscillation or even direction dependent oscillations that you can get from these difference files. And then the stresses that are calculated based on the temperatures and the Bruneian parameters. I heard the sound, I see the done fit all complete, and you can click OK. You can go through and look through all parameters. You see how well the fit was done. Again, sometimes if you do the, for example, zero estimation based on one scan, and then you see some clear pattern. For example, here I see the pattern that here the scan starts early, the fit starts early. Here again, fit starts a little bit early, but there is no crossing. Here it's kind of the same. Here is not the same. Here fit starts early. Maybe I need to check the zero. Here also fit starts early. So I will check the fit, and then I will fit again. Maybe I will change the zero shift, and then if I need to change zero shift, I need to reload the files and then fit all, and then I can either use interpolated files or I can save the files after the fit just as they are. Usually I prefer saving file as they are. Sometimes when I want better resolution of the map, I can interpolate it a little bit. Sometimes when I have non-equidistant measurement, I should interpolate for the correctness of the map. And that's it. And also, if I do not choose save beforehand and files were not saved, I can still save the files based on here, based on this save fit results, save files, save all files, feeds, fit temps. The latest version, I recommend to use this button, save all files. For example, here you can see that right now, let's check our test data sets to temperature model, power dependent. You see that there is no files, but then I can click save all files, and let's see what happens. And as you can see, the files started appearing, the params files and the rest of the files, the ones that I explained. There are some extra files, for example, to temperature modeled is from early emergence or temps files. In temps files, you have the same electron lattice temperature, just all in one file. You usually don't want to have it like that, but this file still saves due to the older versions of the program. We're using those kind of files. Let's quickly go through the file params, which is usually you are interested in this file the most because it's exactly what gives you the fluence dependence of your parameters. So you see it gives you x. The x is exactly the fluences that you have here. For example, 177 is the first one, and here you can plot the dependence of one parameter versus fluence, dependence on another parameter versus fluence. Then you have electron phonon coupling strength G. You have recalculated lambda omega, second moment of Eliasberg function from the Allen's formula. You need to look into 1986 Allen's paper that you will see how to get this lambda omega square based on the electron temperature and these parameters. Actually, it does not use the electron temperature. It uses the Sommerfeld coefficient and this parameter. You can look into the paper how you can do it. And then you have electron scattering time. Additionally, out of these 4 parameters, there are some calculated properties like R-square, which is the goodness of fit. You can see that first fit was not really good. The rest is all above 90. So if you want to delete some fit, you're interested in that, then you have 3 different sum of square errors. There are sum of square errors in different regions of fit, in all focus region, in different parts of regions. Let me show you. So there are focus region, and you can look inside of the focus region, inside of all data from 0 to 300 to check how it changes, or just inside of pre-0, before 0, the sum of square errors, just to make sure that everything is fine. This is more for diagnostic purposes. For statistical analysis, you're interested in sum in goodness of fit R-square. And then you have the properties, for example, the maximum temperature of electrons that were calculated, and then the time x was in picoseconds where this maximum achieved. Then you have the integrated properties that are defined by that integrated region. Then you have the integrated temperatures, both lattice and electron. Then you have maximum lattice temperature and position. But those parameters usually you are not interested too much in those. Those are more diagnostical. Sometimes you want to look in the temperatures too, but usually the parameters that you are interested are only the first 5, realistically only these 4. The electron thermalization time, lambda omega square, which is the second moment of a Linebaugh function calculated from constant g, and then AB thermoreflectance coefficients. So this is how it works. Here you can see that temperature file saved done, everything was saved. You can look into all different files saved. The most important files are parameters, and then you have 2 sets of files. Once with X, you can see with X is for origin or for other programs. Then you can see IgorPro. These files can be opened in the IgorPro, and you can look into the video how to open them in the IgorPro separately.